So we can look at the resonance structures of the molecule once you've added a substituent on it to determine where on the molecule is going to be best suited for adding your next substituent. So what we do here is look at the resonance structures. So I'm going to first draw anisole. And then I'm going to also do nitrobenzene. And then I'm going to give you two of them to do on your own. So we're going to draw resonance structures that include, in this case, we're looking at how the substituent impacts. So we're looking at the secondary resonances. So I'm going to start by drawing those secondary resonances from, so again, we're starting with anisole. Remember, when you draw resonance structures, you maintain the charges. So I have both a positive and a negative charge on my structure to keep it neutral. And then I can keep moving around the lone pair. And so that lone pair from the electron donating group can be distributed around the molecule. And we'll see how that lone pair affects the nucleophilicity of the molecule. And so that's where we're going with this. So I'm going to draw my double bond here. I'm going to have a negative charge here. And so for our secondary resonances, we can see that we're just rotating that lone pair around the ring. And once we're done, we're going to notice that they're only in certain positions. And so I'm going to summarize what we see. So if you notice the electron donating groups, and from your reading you know that they're activators, they add electron density to the aromatic ring. In our case, we're talking about benzene, but it could be any aromatic ring, which makes the ring more nucleophilic and hence react faster. But specifically, when we look at the resonance structures, we notice that the lone pair in the resonance structures are going to end up in the ortho and the pair positions. Now, when we're talking about regiochemistry of our molecules, which I mentioned in class, when we're concerned with our regiochemistry, this is the starting point from which we look at. We will look at what happens to sustain the reaction, but this is what happens in terms of where is your electrophile likely most to collide to form a reaction. And we notice that the lone pair is in orthopair position, which means these are the most nucleophilic centers. Now, there is one other thing with regiochemistry, and I'm just going to briefly introduce it. It will come up in some of your practice problems. Statistically, there are two ortho positions, which means statistically they're twice as likely to have a collision. Now, that then should mean as long as my substituent is small, and we'll say why that is important later, as long as it's relatively small, like a methyl group, an OH group, things like that, as long as they're fairly small, you should get twice as much ortho as para, because statistically it makes sense. However, the para is more out of the way. And so from a steric perspective is the better structure. So as your substituent gets larger and larger and larger, it's easier to put things in the para position to avoid sterics. And so energetically, the para is favored from an energetic standpoint. but really only makes a huge, that energy really makes a huge difference when we're talking about really large groups. So it becomes a bigger issue with large groups. Now, in terms of the electron withdrawing groups, I'm going to be using nitrobenzene. Since that is one of our strongest electron withdrawing groups, you have a plus charge near the ring. The electron density is actually going to be pulled up into it. And so where our charges are, we're going to notice something. So instead of having negative charges in the ortho and para position, what we do notice is that we have positive charges in the ortho and para position, which tells us that those positions with electron withdrawing groups, and electron withdrawing groups we know pull the electron density from the ring, so they deactivate the ring and make the ring slower to react. However, because the positive charge is in the orthopara, that means that those positions are less nucleophilic. It doesn't mean that they don't react. Just like in our previous example, the meta does react. It's just going to be a very minor product. In this case, our orthopara is less nucleophilic, so what's left is the meta, and so the meta is going to give us our major product. And so, with one exception, electron withdrawing groups are going to give us major, the meta as the major. And so we call them meta directors, but you also still will get a little bit of the orthopara, and electron donators are orthopara as the major, and so we call them orthopara directors. So essentially, that question I'm going to ask you is basically asking you to explain the same thing. There is an exception, and that's going to be one of your questions. Is there's one exception to that rule, something that's electron withdrawing but is an orthopara director, and it has, the reasoning is actually related to these resonance structures. And then later on we'll talk about how we sustain the reaction. So once you get the collision, then you have to look at the sigma complexes resonance structures as well.